Okay, so now going back to our other thing. We have done this. Check. And now we have to do the other thing, which will lead us directly to lasers, I promise. So now that the whole field of quantum mechanics has been developed, we are not going to talk about lasers. Here we go. So number 2. Atoms in thermal equilibrium. Boltzmann distribution. And I'm going to try to draw let's see how good this goes. Arrays are just a bunch of similar things joined together. For example, you are an array of physics 401. You are individuals, but we bunch you guys together between 10 and 11:30. We make an array out of you, and that array is called physics 401. Okay? So atoms also can be grouped in arrays. There could be multiple things that could happen. For example, one of the things that's important is atoms that are at the same temperature. They could collect together. They will have similar kinetic energies. They will have similar potential energies. You know, you can group them together. Atoms in this room, the molecules and atoms in this room, have to be at the temperature of the room. What happens to them if they're not at that temperature? We input more energy into the system so that they all are, correct? If the environment changes outside, what happens to the atoms inside the room? They will try to match that environment. Say if the environment gets really, really cold, what will the atoms in this room want to do? Be in thermal equilibrium with it? In order to raise this room's temperature, what do we have to do? Put more energy into the system, right? Or what if the temperature outside goes up? Then we have to take away energy from this room in order to decrease the temperature, correct? When both are at the same temperature, we call it thermal equilibrium. I mean, equilibrium could be of many kinds, but this particular one is called thermal equilibrium. Good? Okay, so now let's write this down. So in an array, which is also sometimes called, you'll see this word assembly of atoms in thermal equilibrium, say at temperature T, the likelihood, say Pi, that a given atom in this array or assembly will be in one of the states of energy EI is given by Boltzmann distribution. And when we get to thermal, we will talk about more distributions beyond that, like the Fermi-Dirac, the Bose-Einstein. But this is fundamentally where all of those distributions came from. So fascinating. I wish we could talk about all of it in terms of history instead of categorizing them in terms of subject matter. That would be so fascinating, just to see where all of these things came from. Okay, so what's the formula that Boltzmann gave us? Ready? Pi equals P1 or P0 e to the minus E1 E Actually, I'll do EI minus E1 divided by KT. Sometimes also subscript KBT. Where, do you remember where KB came from? We did it here. And now I'm going to define it for you. Ready? KB, well, let me put a box around this. This is kind of important. Okay, where KB is called the Boltzmann constant with a value of 1.38 times 10 to the 23 joules per Kelvin, or 8.62 times 10 to the minus 5 electron volts over Kelvin. So if you do not write it on the exam, here's my hint for you. What is an electron volt? It is the charge of an electron through 1 volt. So what's the charge of an electron? And what is 1 volt? That's what it is. So 1 electron volt is the energy that 1 electron gains when it goes through one volt. By definition, an electron volt, remember this, is the energy that is gained or lost by an electron when it goes through 1 volt. T will always be measured in kelvins. And how do you get kelvins? 273 plus temperature in Celsius. Pi or P1 is the likelihood that the atom is in its ground state.
Wait, P or P1?
P1. Pi is any likelihood for any state. You can call it 0 if you want. Don't call it 1. Just call it P0. The reason why I'm not using Pi because I need it for something else in the future.
I just didn't know. You said 1 and I, so.
No, so P1 is the likelihood that the atom is in its ground state. Sometimes also called P0, if that confuses you. Okay? And in its ground state, the energy is E1 or E0. However you want to say it. So if you want to do E0, just replace E1 with E0. Remember, in the ground state, the energy doesn't disappear. It'll still have energy. It just won't have any energy that it can give away. Won't have excess energy. What did Boltzmann write? So I'm going to now define Boltzmann distribution in words. He said, in thermal equilibrium, atoms are more likely to be in states with lower energy. So he modified this likelihood equation, let's call it equation 1, to this new equation, which now we're going to call Boltzmann ratio. And sometimes it's also called relative population. And he redefined it to say N2 over N1 will be given by minus E2 minus E1 over KT, or E to the minus HF over KT. where E2 minus E1 is defined as HF. Okay, are we ready? Think about lasers. This will lead us into it.